Hello, good morning, everyone, and respected teacher. My name is Manikant Reddy from Section A Cybersecurity. Today, I'm going to teach you about extension of 105 Caley-Hamilton theorem and procedure for computation of the drazin inverse matrix with the subject of linear algebra and calculus. First, uh, we'll look at about Caley-Hamilton theorem and how to computation for drazin inverse matrix. So we'll look at about into this video. So here is the topic: extension of Caley-Hamilton theorem and procedure for computation of drazin inverse matrix. Okay, here. Uh, Here is the one mathematician called Arthur Caley. Is a widely regarded as a Britain leading pure mathematician of the 19th century. Caley in 1848 went to Dublin to attend lectures on a quaternions by Hamilton. They discovered later Caley impressed him by being the second to publish work on them. Caley proved the theorem for matrices of a dimension 3 and less, publishing proof of a two-dimensional case. As for n into n matrix, Caley stated that I have not thought it necessary to undertake the labor of a formal proof of the theorem in the general case of matrix of any degree. Okay, and this one, this fellow William Rowan Hamilton. This in the previous slide we saw that incident about Caley and Hamilton. Here is the one Hamilton, William Rowan Hamilton, Irish physicist and astronomer and mathematician. For the foreign member of American National Academy of Sciences, while maintaining an opposing position about how geometry should be studied, Hamilton always remained on the best terms with Caley. Caley proved that for the linear function of a quaternions, there exists a certain equation depending on the linear functions that is satisfied by the linear functions itself. Okay. Here, two scientists is there, Caley and Hamilton. Both discovered this Caley-Hamilton theorem. Just we will know about Caley-Hamilton theorem, what is the uses, and about we'll dive into the topic into more. Okay, here the classical Caley-Hamilton theorem says that every square matrix satisfies its own characteristic equation. The Caley-Hamilton theorem has been extended to rectangular matrix, block matrix, pair of block matrices, and standard and singular two-dimensional linear systems, 2D systems. Uh, in Kaczorek, the Caley-Hamilton theorem has been extended to n-dimensional real polynomial matrices. An extension of a Caley-Hamilton theorem for continuous time linear systems with delays has been given in 8. The Caley-Hamilton theorem has been extended to fractional standard and descriptor continuous time and discrete time linear equations. The Caley-Hamilton theorem and its generalizations has been used in a control systems, electric circuits, systems with delays, singular systems, 2D linear systems, etc. The drazin inverse matrix method for fractional descriptor continuous time and discrete time linear systems has been introduced in 15 and 16. In this paper, Caley-Hamilton theorem will be extended to drazin inverse matrix, and procedure for computation of a drazin inverse matrix will be proposed. Okay. Here, actually, what is mean by Hamilton theorem? What it says is means uh, it's third is both mathematician says that every square matrix, only square matrix, not a rectangular matrix, only square matrix satisfies its characteristic equation. Okay, here what is mean by characteristic equation, and just we'll look at it. Characteristic equations. Okay, next slide we'll go. Yeah, we may compute the inverse matrix. There have been following procedure for drazin inverse matrix. Here is the procedure to find a drazin inverse matrix for any matrix, any square matrix, mainly square matrix. Step one is use one, compute the index of a matrix E per D. Step two, compute the coefficients K equal to, here is the step two, and step three, compute the matrix 15 and check the condition. Step four, compute the coefficients. Step five, using 20, compute the matrix 1b, and using 17, compute the drazin inverse matrix. Here is some procedure to find drazin inverse matrix. So for the slides, some example, I will explain with some examples, and it may be clear about it. Okay. Okay. Here is the one problem, and statement also is there. Hamilton theorem. Here is the statement says that every square matrix satisfies its own characteristic equation. Okay. Here's the statement, and first example or any problem. So first question is, show that a matrix A. Here is a matrix given 3 into 3. Only square matrix only allowed in this Hamilton theorem. First, here is the this one no column and row. This is a rows and this is a columns. Uh, uh, Position A11 and A22 and A33 like this. Uh, Satisfies its characteristic equation. Hence, find A inverse. Here, topic is there. Uh, Hamilton theorem and computation for drazin square inverse matrix. Here's the same problem. First, satisfies Hamilton theorem and find A inverse. Okay. First, here is the characteristic equation of A is that of A minus lambda I equal to 0. Here I is a identity matrix. Yes, A is the given matrix and lambda is a variable and I is a identity matrix. Okay, this is the one characteristic equation. Starting onwards, Hamilton theorem main statement is every square matrix satisfies its own characteristic equation. Okay, here own characteristic equation means what? Here is the equation A minus lambda I. This is a characteristics. Here is there no delta of A minus lambda I equals 0. This is a characteristic equation. Okay. Next, we'll see about this solution and understand Hamilton theorem and how to find a inverse through Hamilton theorem. Okay. Here, many ways to find a inverse, like so many methods are there. Here is the Hamilton theorem is a one process here. Okay. Given a given matrix, here is there lambda cube minus lambda square plus lambda minus 1. Here, how we got this? By solving det of A minus lambda I. By solving characteristic equation, we get this lambda cube minus lambda square plus lambda minus 1 equal to 0. Here by Hamilton theorem, we have a just wherever lambda is there, we put A, because Hamilton theorem says that every Square matrix satisfies its every square matrix satisfies its uh, own characteristic equation. This is a characteristic equation, and this is a A. Every square matrix is a square matrix here is A and satisfies its characteristic equation. So we'll substitute in this. Here, what is there? A cube and A square plus A minus I. Okay. Uh, we have only given that A is a matrix. Matrix is A is given, and we have to find A square and A cube, and we know that I is a identity matrix. Okay, first we'll find that A cube. A cube means what? How to find that? A into A. Here is given A and into this matrix. First A matrix and into that matrix only. We get A square matrix. Here's the A square we get now. A square into again we multiplied with A. We get A cube. I hope you know that how to multiplication of matrices. Okay, need not be teach that multiplication of matrix in this lecture. Okay, here we know A cube, and here is A square, and here is A. Okay, we substitute these matrices in this equation, characteristic equation. Uh, okay, characteristic equation, we found this equation. In this, we found A square and A cube, and we substitute this. Okay. Uh, Here main theme is this value must be 0. This value must be 0. Main okay. After substituting A cube minus A square plus A minus I means what? Diagonal elements must be 1, and upper triangular and lower triangular elements is must be 0 here. Whatever symbol is there, that we will do. Okay, -1 minus of -1 was 0. 1 0 here. First element we will we will do -1 minus of -1 0 here, and +1 of -1. How much? 0 0 0 0. First A1 first element we get 0, and second one will say A 2 is there, minus 0, only 2 we get, and plus of minus we get minus 2. 2 minus 2 here, second element what we get? 2. Sorry, 2 minus 2, second element what we get? 0. Like that, all elements must be addition and subtraction will do. We get 0 matrix, null matrix. Okay, 0. Here is the equation, and multiply with A inverse, we get here A square minus A plus I equal to A inverse. How we get this? Let's think about it. Multiply with A inverse on both sides. Both sides means what? A cube into A inverse, and minus A square into A inverse plus A into A inverse minus I equal to 0. Equal to 0 into A inverse equal to 0. Huh? Okay. A square into A inverse. A square, A square here. A into A inverse, I into A square, only A square we get. And A minus A into A square, no? We get A, and A into A inverse, identity matrix, no? Okay, minus A. And A into A inverse, we get, no? I into A inverse, what we get? A inverse only. Minus A inverse, we transfer on right side. What we get? Plus A inverse. Okay. What we get? A inverse we have no. This values also are there here. A square value is A square matrix is there. A matrix is there. Identity matrix also is there. What we get? A inverse equal to A square. A square means what? -1 0 0. This matrix is there, no? There. Okay. A square minus A matrix. A matrix here is given now. We substitute in this plus identity matrix. Here -1 of -1. -1 of -1 0. 0 plus 1. Sorry. -1 -1 -2. -2 plus 1 -1 here. Okay. All elements we as it is we do same thing. We get A inverse matrix. Okay. So we'll go into next problem or problem here. Problem verify Hamilton theorem of a given matrix 1 2 3 2 4 5 3 5 6 elements are there. Hence find A inverse. Same as this problem. Suppose you try in previous method, and this is another method. This method linear dependence and independence of vectors will involve. Show that vectors first row 1 2 3 and second 3 minus 2 1 and 1 minus 6 5 from a linear dependent side. Okay. Sure. The vector x1 x2 x3 is there here, and find here A matrix. Okay. Just combine all these matrices. Here is a one problem for homework only, and second one topic linear dependence and independence where we can will solve. Okay. Yeah, this much. Linear dependence means what? Det A equals 0. Linear independence means what? Det A not equal to 0. That much only. You know all these how to find a determinant and okay. Thank you. Thank you so much.